Hello everybody, Tarmo Ramel here again, and today we're going to talk about some discrete probability distributions. Specifically, we're going to talk about the binomial distribution and the Poisson distribution, and these are going to allow us to answer questions where we have outcomes that are discrete, that is, they can be counted. So if we start off with the binomial distribution, we talk about binomial experiments. These are where we tend to have outcomes that are classified as either successes or failures. So think about taking a multiple choice test, and on that multiple choice test you may get the answer correct, that's a success, or you may answer the question incorrectly, that's considered a failure. So what we can do is set up some basic symbols and terminology that will allow us to work through an example as I have here on the screen behind me. So if we look at the first row here, P and in brackets S is the probability of successes. It's the symbol that we use to represent those successes. And it is also represented by the lowercase p, which is the numerical probability of those successes. So we talk about, the probability of success, p, and in brackets capital S, but when we actually give it a value, that value is going to be lowercase p. We also have the symbol for the probability of failure, p, and in brackets F. And we can simply calculate that as the difference between 1 and how much probability was a success. So if our probability of success is 30% or 0.3, then the failure must be 70% or 0.7. So we simply subtract from 1 and we get the difference. So in that case, the probability of failure is 1 minus p, which is equal to q. So we call Q the numerical probability of failure. So if the probability of success is 0.3, then Q is going to be 0.7. We also identify N, the number of trials, and X is the number of successes in those N trials. That sounds like a lot of words to pack in your mouth, but let's work through an example where we can see what these things actually look like. This example comes to us from the textbook, but I'd like to work through it step by step to show you how we might do a question like this, or how we would work through a question like this in Excel should we have to do it on our own. A coin is tossed 3 times. So we have 3 different trials. Find the probability of getting exactly 2 heads. So we can work through this in this classical sample space method where we could actually perform the experiment where we take a coin and we toss it. We write down, did we get heads or tails? We toss it again. We write down whether it's heads or tails. We toss it again. We get heads or tails. But the results are discrete. We don't have a continuous variable. These things are either heads or tails. They have a category that is either one or the other, and we can count how many times they happen. So we could flip these coins and get 3 heads. So we flip it, we get heads, we flip it, we get heads, we flip it, we get heads. Or we might get heads and tails, or heads, tails, heads, tails, heads, heads, and so on. There are these 8 possible outcomes, and we know that the 3 that are highlighted here in orange are the ones where we have exactly 2 heads. So 3 heads doesn't count, 1 heads doesn't count, no heads doesn't count, but where we have 2 heads, those count. So in the classical sense, we would have, you can see in the formula bar, 3 over 8 gives us the probability. We can see that it's in the cell here as an equation as well. That's great when the number of successes and trials and everything are small and easy to work with, but sometimes these numbers get to be larger, and it's nice to have a formulation that allows us to get at that answer in a much more simple case. So we could take this same question and work it through the sort of binomial experiment method rather than working through the sample space method, and show you how it works. And the nice thing is, once you enter the formulations onto your Excel worksheet, if you ever have a similar question where the numbers are different, you can plug the numbers in and have the calculation automatically solve the question for you, and then you just change the wording and make it look the way that you want it to look. I'm going to show you to solve this as a binomial experiment. The textbook and the lecture notes provide you with the binomial equation. It's given here, and it looks a little bit daunting, but we can work through it if we know what the terms are that we might need. They are n, x, p, and q. Remember, n is the number of trials, x are the number of successes in those n trials. We have p, which is the numerical probability of a success, and we have q, which is the numerical probability of a failure. So n is the number of trials. We have a coin, and we are going to toss it 3 times. So we put the number 3 into this cell, and if we have the variables and we have their values, then it becomes really easy to substitute them into the equations as necessary. X is the number of successes in those trials. Remember, we want to have exactly 2 heads. So we put now the value 2 into this cell. Now, P is the probability of success. Well, when you toss a coin, you have a 50-50 chance of getting heads. So it's 1 over 2, or 0.5. And Q is, in this case, it's also going to be 0.5, because 1 minus 0.5 gives us 0.5, but we can put that in as a calculation so that if ever those values were to change, they would update automatically. So in this case, it would be 1 minus the value that we have in N15, which is the value that we had stored for P. So we have now values for N, X, P, and Q. We can take these values and we can substitute them into this formula. So I've inserted these onto the worksheet using the equation editor in Excel. And what I like about this is it allows you to see the calculation the way you would see it if you were to work it out with pen and paper or pencil and paper in sort of a traditional format. So we have the equation in the first version here with the symbols or the variables in them. And all that I have done is gone in the second version. I took the first one, I made a copy of it, pasted it down below, and then went in and changed all of the x's to 2's. I changed the n's to 3's. I changed the p's and the q's to their corresponding probability values. So all of that is simply to show your TA or to me, or to remind yourself of how did I get from that first step to the second step. And it's always really nice to do that, even though we can get to the final answer in a single cell. By showing your work and illustrating how did you get those values and where did they come from, things become a little bit easier to understand, to follow through. So once we have this, we could take a calculator and we could punch it in and get the answer. We can do the same thing in Excel, and I've done that here. So the probability of getting exactly 2 successes gives us 0.375. The equation is in the equation bar, but if I double click on here, you can see that what I've done is I've simply written the equation as we see it up here in sort of a linear Excel format. And it gets a little bit busy and hard to think of. Sometimes what I like to do when equations get really large is I like to take the top of a fraction and solve it in one cell, take the bottom of a fraction, solve it in a second cell, and then divide the fraction to get the final answer in a third cell. All of those things are possible. This is simply one way of doing it all in one step. So we are using the fact or the factorial function as it shows up with the exclamation point notation in the equation. The chevron, or this caret, tells us that we have an exponent, and we've just copied the proper values into the calculation or the equation, which is still a very manual method of doing this question, which might not be the most efficient, because if I went and changed the values for n, x, p, and q up here, they wouldn't change in this calculation because I've hard-coded them by typing in those values. So what I have is this additional version down here, where if I double-click on there, you can see that what I've done, in fact, is I've pulled the values from the list that we have live on this page. So anytime that I want to calculate n factorial, I take the value from n13, and you can see that it's color-coded in blue so that it's very easy to see where that value is coming from. So all I've done is I've replaced the values with a cell reference from where the values are coming from. And this is really great. We can see that it gives us exactly the same result. But if I ever went in here and I changed the initial values, my answer will also update. So rather than flipping the coin 3 times, imagine that I want to flip it 10 times. I simply change the value in that cell and I hit enter, and notice that my probability here updates. Obviously, this doesn't change. I haven't gone and manually changed all of those. This equation is never going to change because those were all hard-coded values. But the equation that is linked to the input values changes instantly. So if I ever had another question where I needed to perform a binomial experiment, and I already have this calculator built and ready on my screen, I'd be able to reuse it and then just change the annotation and change the wording to make sure that everything on that question on that page aligned nicely. So I'm going to put this back to 3 just so that things don't look all messy. But that is how we solve a binomial experiment. Set up the terms, figure out these 4 values, insert the equation, work it out long form, annotate, and Bob's your uncle. Well, maybe he's not, but he's somebody's uncle. Anyhow, binomial distributions. The second thing that I want to talk about today, and I'm going to go to the second tab, and of course I'm in the middle and blocking it, but down here we have the Poisson tab, and I'm going to click on there to open up a second worksheet. And then I'm going to come back because then you can see who is doing the talking today. Okay, so when we're talking about Poisson distributions, we're talking about another discrete probability distribution, but when n is large and p is small, and specifically when the independent variables occur over a period of time. Now, sometimes time, but it could also be used when items are distributed over an area, in a volume, or through time. So the wording of the question becomes really important in identifying whether or not we can use a binomial distribution or can we use a Poisson distribution for the kinds of analyses of probability that we're doing. So you could think about the number of plants growing per hectare, the defects on some length of videotape, the number of molecules in a container. Any of these things tend to be distributed in space, time, or in a volume. They are highly suited for a Poisson type of distribution. So let's work through another question. But it requires us to know this special value, the stylized lowercase e. It's called the Euler constant, Euler spelled with an E, and it is approximately 2.7183, and just like pi, it continues indefinitely, but we generally take the first value plus 4 decimal places. Gives us a great sort of representation of this value. But the nice thing is, working in Excel, we can go to much greater detail by using this value not as typing in 2.7183 on our keyboard, but by using the function exp and then a 1 in brackets, and it gives us this constant that we can then use and position within the calculation as necessary. We also need to know something called lambda. Lambda is the Greek letter depicted here. It's also used for wavelength if you end up taking remote sensing. But again, this is a value that's used in this calculation. And it's designed to mean the average or the mean number of occurrences per time or volume or area or whatever that base unit is that our data is collected in. So let's take a look at an example. We have here, and I'm going to zoom in just a bit because I feel like it could be a little bit larger. We have somebody who grows grapes for making wine. So a wine grower is aware that 50 randomly distributed vines in their vineyard have a disease, and their vineyard is 600 hectares in size. So find the probability that any hectare in this vineyard has exactly 2 diseased vines. So we have lots of information packed in here. What we want to do is start to pull out the pieces that we need to plug them into the Poisson distribution. We know that we've got something distributed over an area, and we have a relatively large number. It means that this is something that is quite suitable for a Poisson distribution. So the Poisson distribution is given in this form if we were to write it out, and we have, as we can see, the Euler constant, we have this lambda value, we have x. So what we really want to do is get a listing of all of the variables that need to go into the calculation. In this case, lambda and x. We know that e is a constant, and I already have it calculated and provided over here. I could, to be nice and clean, I could go over here and add it just so that it's all neatly in one place. I put in here exp1 so that all of the values that we're working with are in one location. I'm just going to reduce the number of decimal places there just to make it look nice. So then again, we have our original equation. I'm going to substitute the values that we have up above into this equation down below to show that substitution in terms of showing my work and showing where things are coming from. Now I'm just going to scroll my page just a little bit just so that we can see this work down here in a little bit of a better fashion. And I'm going to show you how we can calculate this result in 3 different ways. The first one is being manually. And that is, if we were to double click on here, we can see that the format of this function is now worked out linearly, and I have manually typed in each of the values for lambda, x, and well, I didn't do e, but I could have actually, instead of exp1, I could have typed in 2.7183 in this location as well. And when we run that, we get 0.00317. There's our answer. That's the probability that we would have 2 vines in any hectare that have this disease. It's a really low probability. We could refer to the cell referencing method, and we can go in here, and if we double click, we can see that it's taking the value for lambda from up above, and it's taking the value for x from up above as well, and it's substituting those in so that if we ever change those up above, the calculation would also change. I realize I forgot to show you how we arrived at lambda. We know that 2 is the 2 diseased vines. That's the outcome that we're looking for. But how did we get lambda? Let's go take a quick look. If I double click on there, we can see that this is the average number of vines that are diseased. We know that there are 50 of them distributed in this 600 hectare vineyard. So 50 over 600 gives us this average value per hectare of 0.08. Relatively simple and straightforward. The nice thing is Excel allows us to do one step even more simply this calculation, and that is using the built-in equation. So if I double click on here, we can see that we've got this function called Poisson, and Poisson, we can then simply grab the values for x and for lambda, and we put in this term false just to make it run correctly. The constant is already known, so it's used inside the function, so we don't need to provide it specifically, and we get this exact number. Now, you're looking at this and saying, why is this 0.00317 and these ones are 0.00319? Remember that when I did this manually, then I put in 0.083. I typed that in manually, but I truncated all of the remaining little bits of values that may continue on, whereas using the cell referencing system and using continuous variable ranges, the precision of the values that go into the calculation is a little bit higher. So there's going to be a little bit of a difference as you get to sort of really far down into the decimal places. These can all be made to look exactly the same by rounding them to some reasonable number of decimal places. Usually we would show decimal places for probability at, let's say, 4 positions, but again, both of these answers are correct if we know how you got to them, what values you used, and so on. Keep in mind that if you use the built-in or the cell reference versions, that when you alter the values up above, everything automatically updates for you. However, putting in these kinds of examples of what you did in each step allows us very easily to follow through with your work. So when you're submitting work, it's totally fine to work it through with a built-in equation or to build the calculation and use the cell referencing, but tell us what you're doing. Show us the work that you're doing. Put the annotations and the calculations into your work, and it will be a much more complete result. And then also at the end, don't just leave it like this, but have a concluding statement. Tell us, therefore, the probability of having 2 diseased vines in any given hectare is probability of 0.0032. That is a nice complete answer. Make sure that things are easily found on your page so that we don't have to go looking for them. Until next week, have fun, build yourself a calculator, something that's going to help you redo these kinds of questions on midterms, final exams, at your first job, maybe when you're doing work for another course. Talk to you soon.